M1 Lesson 20, we're going to be looking at solution sets to equations and inequalities with two variables. This lesson is going to come with two outcomes. One is to recognize and identify solutions to a two-variable equation, and then to represent that solution set graphically. And our second outcome is going to be create two-variable equations and their graphs to represent a given situation. So in exercise 1, the students were given an equation such as 4x minus y equals 10. And they had an opportunity to pick out from this limited list which ones would be solutions to this given equation. So for example, if we looked at the first one, maybe someone thought 3 comma 2 would be a solution to this. So what the student needs to identify is that this is an x and that's a y. So then they would come to this equation and say, well, 4 times 3 minus 2. The question is, does that equal 10? So 4 minus 3 is 12 minus 2. We're still asking ourselves, does it equal 10? So then 12 minus 2, that's 10, is equal to 10, and that's true. 10 does equal 10. So in class, what the students would do is they would come up to the board, and if they believe it's a solution, they would put it down here in the solution box. And so then the student might try another one. Perhaps the one that says 2 comma 3. So if we erase this part here and go back in, let's say this is x and this is y. And so this time we say 4 times 2 minus 3. 4 times 2 is 8. We subtract 3. So 8 minus 3 is 5, which does not equal 10. So therefore, in that case, this one would not be a solution to the given ordered pairs. So when the student would go and drag this in, it would come back out as part of their opportunity to learn which ones would be solutions versus which ones would not. So again, we would encourage the students to work through each one, either in pairs or individually, and ultimately the ones that work are the -1, -14, the 1, comma -6, the 5, 10, and the 0, -10. Again, the other ones don't work. For example, if a student thought this one would work, they would come up to the board, they would go in, but it would snap back because it would not be a given solution to this particular equation. So given those solutions, we take that anticipatory set and we carry over into this particular exercise here. And part A, it says, discover as many additional solutions to the equation 4x minus y equals 10 as possible. So again, we're encouraging students to then take and say, well, what else might work? So one way to think about this is if I had the 4x minus the y equals 10, and let's say I wanted to know what about when x equals 1. Well, in that case, we would write 4 times 1, well, minus y equals 10. So 4 times 1 is 4, minus y equals 10. Subtract 4 to both sides. Negative y is equal to 6, and so if I divide by -1, then I know that an additional value would be y equals -6. So as a point, we would say 1 comma -6. Again, noting that in my example there, this was one of the ones chosen right here. But then we would encourage the students to try some other values of their choice. This will be given and done in small groups, so enough time for students to kind of think it through and come up with some ideas of what they think some additional solutions would be. Part B said, now find 5 more solutions where one or more variables are negative numbers or non-integer values. Be prepared to show strategies for this. So for example, if we're looking at that 4x minus y equals 10, what about if I chose 1/2 for x, or x equals 0.5 or 1/2? Something that falls in the non-integer category. Well, we could do 4 times 1/2 minus y equals 10. Well, half of 4 is 2. Let's back that up. Let's see, minus y equals 10. So I would subtract 2. So negative y would equal to 8. And so I divide by negative 1. And y would equal negative 8. So we know that an additional point would be 0.5 comma negative 8. And so maybe if we ask the students to graph that, would be down 1/2, then 1, 2, 3, 4, 5, 6, 7, 8. And so that point would be located actually right here on this side, over 1/2, and then down 8. The students, again, are encouraged to find multiple answers. There are plenty of them that work. 0.5 is just one of them that can be used. And again, the teacher would encourage students, don't forget the negative numbers. So maybe something like negative 1 or negative 2 or negative 3 or negative 1/2 and so forth, to see what those particular values may end up being. In part C, they want to know how many ordered pairs x and y will be in the solution set for this value. We're hoping the students would say that there are infinitely many, or what we might say is all real numbers. In other words, it doesn't matter what I choose for x, I'm going to get a y value. There will be a point on the graph that is going to end up being graphed. In part D, it says create a visual representation of the points. So if we look at some of the points that showed up from the last slide, 1, 2, 3 over 2, so 3 comma 2, again, where are these points coming from? It's from the slide with the anticipatory set. So here was 3 comma 2. Maybe if we look at 1 comma negative 6, so 1 and then negative 6 is here. If we choose another point, maybe 5, 10. So 1, 2, 3, 4, 5. 10 is going to be up here off of the graph. That'll be up here in this general idea. What we're hoping the students get a sense of in this particular perspective is whenever we go in and draw a line or try to connect the dots through these points, the students will observe that we have a linear pattern that is occurring through these given points. And so it's an observation that we want the students to make, because again, if we go back and look at part C, how many ordered pairs x or y will be in the solution set for this given equation? Well, it comes down to the idea that I can put points infinitely many times on this blue line, and even in between these orange dots, I can go in between and add more dots until ultimately we would create that line. And so that's where the idea of all solutions are all real numbers. And in part E, this teacher would ask, why does it make sense to represent the solutions to the equation 4x minus y equals 10 as a line in the coordinate plane? And really the student's answers that would come down to would say, well, there's no way we can plot every single point or every single solution. So the easiest way to represent every single solution is to draw a straight line through the various points we have found to thusly represent every single point that we could potentially solve in this given representation. 3, the sum of two numbers is 25, what are the numbers? So in this one, the question says to create an equation using two variables to represent this situation. Be sure to explain the meaning of each particular variable. So typically the one that students are going to come up with is they're going to say x plus y equals 25. To represent this, any sum of two numbers is 25. So in part B, we're giving the students the opportunity to list at least 6 solutions that can sum to equal 25. And so a lot of times the students will start, well, 25 plus 0 is 25, and then they'll say 24, and then 1, well, that equals 25. And so we can continue to list as many as we want. The teacher's going to encourage to list 6. So during this discussion, the teacher may also prompt the students to think, well, what if I had 14.5 plus what would equal 25? Or the teacher might say, what if I had negative 6 plus y equals 25? Just to kind of spur on that discussion of negatives and decimals being a part of that given situation. And then finally, the students would be encouraged to graph a solution or a line based on this particular equation in that design. In example number 4, it brings up a more specific scenario. It says Gia had 25 songs in a playlist composed of songs from her 2 favorite artists, one of them being Beyonce, the other one being Jennifer Lopez. How many songs did she have from each one on the particular playlist? So again, we bring in this scenario from the last one where, again, the sum of two numbers is 25, whereas here we have an actual scenario. And in that scenario, the student's going to acknowledge and think the same thing. X plus y equals 25. And so that's the creation of a scenario. And this is list at least 3 solutions in what you design. So again, the student might say, well, maybe I've got 10 of one song and 15 of another song, and that would equal 25. Or they might say I've got 20 of one song and 5 of another, that equals 25. And so then the teacher might say, well, what if I've got 25 of one? What does that mean for the other? That means I would have none. Now, the question to think about here is in part C, when we create a graph to represent the solution, it's not so much in the graph or the design, but the question is, what would this graph look like? In other words, the teacher is encouraging the student to think, can I have 25 and a half Beyonce songs? Well, I shouldn't say 25 and a half, but let's just say, can I have 15.5 songs of one plus 14.5 songs of another? And so the students would need to be able to reason, well, that doesn't make sense in this particular scenario because I can't have a half of a song from Beyonce or Jennifer Lopez. I either have the whole song or I don't have any of the song. So in the design or the perspective of this, between the last example and this one, the last example here, the students are encouraged to realize that all of my answers are a straight line. Whereas the appropriate thing to say here is that all of my answers would need to be in dotted formation or dots along the line because I can't have the half versions of the half songs in that given piece. Finally, exercise 5, that's what we did. Compare your solutions to exercises 3 and 4. How are they alike and how are they different? And so in exercise 3, we stated that it would be a line that would represent all numbers. That would include decimals, wholes, integers, and so forth. Basically all the real numbers. Whereas in example number 4, we noted that it doesn't make any sense to have half of a song. And you can't have negative songs either. So we're really looking at a case where you have a dot every so often to represent that nice point along the graph, to where these would be whole numbers in this given particular scenario, or you might say the positive integers, which is a subset of the wholes in that particular piece. In closing, the students need to understand that an ordered pair is a solution to a two-variable equation in which each number substituted in its corresponding variable makes the equation a true number sentence. All of the solutions to a two-variable equation are called the solution set. Each ordered pair of numbers in the solution set of the equation corresponds to a point on the coordinate plane. The set of all such points in the coordinate plane is called the graph of the equation. And so it's possible in class, as part of the closure, the teacher may have asked a few additional questions, such as, is the graph of the line y equals 2x minus 3 the same as the solution set to the equation of 2x minus 3? And we would say yes, one is just an image and one is the actual solution sets. Then it says in this one, suppose I am using the equation to represent the following context. The number of trucks manufactured is always fewer than twice the number of cars manufactured. Does it make sense that every single point on the line is a solution? And so again, here the answer would be no, because we can't build a half a truck or a three-quarter truck and sell that truck. That truck will still be considered in production. And so the last one, why is it useful to represent the solutions to a two-variable equation using a graph? Sometimes it's easy to identify shape or distinction or design or curve, or in the feature of a straight line versus points in particular locations can identify to a student what this graph is representing.